Okay, guys, I forgot to show you my guest. This is Buford, the Baylor Bear, and this is Guinevere. They're taking your guys' places till you come back at the end of the semester or in August or whenever you come back. These are my stand-in students, right? They're cute. They keep me from going crazy like I'm going insane. I have something to talk to, so I'm going to put these right here. Put them right here, right? So they're looking ahead, right? Okay, those are my guys. All right, so now that we have that out of the way, now that you know who Buford and Guinevere are, Genevieve. Let's get started with our lesson for the day. All right. So last time, if you guys remember, we were talking about eigenvalues and eigenvectors. So I brought this up for the first time, right? We introduced the idea of what an eigenvalue and eigenvector is. Which is what we have this non-zero vector, and we have this scalar, right? And then we have to figure out how to find eigenvalues and eigenvectors, and that was a lot of fun. You guys enjoyed that so much, I know, right? So I want to do some more examples of eigenvalues and eigenvectors, okay? 3x3 and 4x4. If that doesn't sound exciting to you, you can skip this video or move ahead a little bit or anything like that. And then just do some more examples, just to kind of get a better feel for how these work, all right? So let's get started. So today, we're still in section 7.1, 7.2 now, eigenvalues and eigenvectors. Okay. Topics for the day. We're going to have more eigenvalue examples. And then two, we're going to look at, last thing, just some properties of eigenvalues. And eigenvectors, of course. Okay. Just to conserve space, I'll just say eigenvalue examples and properties of eigenvalues, but what I mean by that is I'm talking about both properties of eigenvalues and eigenvectors, and then examples of eigenvalues and eigenvectors, right? So let's get started where we left off, all right? So first example, I want to do a 3x3 example this time. Find the eigenvalues and eigenvectors of A equal to 1, -1, -1, 0, 1, 3, 0, 3, 1. So let's look at this. Find the eigenvalues and eigenvectors of A equal to 1, -1, -1, 0, 1, 3, 0, 3, 1. We're going to talk about eigenspaces after this example. Talk about what eigenspace is. Okay. All right, so this is my first example for the day. It's a 3x3. So we should get 3 eigenvalues when we do this 3x3 example, right? Now, those eigenvalues could repeat. It could be the same value, or it could have distinct values. We're going to look and see what we have in this particular case, right? So our first step, just like we did before, I'm going to see if I can squeeze that in here, just to kind of conserve a little bit of space. Got to be a little bit careful here. Step 1. I want to solve the characteristic equation. Remember, that was when our determinant is A minus lambda I, right? A minus lambda I, okay, equal to 0. And let me just double check to make sure that it's actually recording. So bear with me a little bit. Just gotta make sure I'm not talking to myself for an hour. Okay, it is recording. Good. There's nothing worse than talking to yourself for an hour, then you have to reteach it again. You're like, man, I just got to teach this. Okay. Anyway, so I want to be able to find the characteristic equation, solve for lambda, right? That's what we're going to do, solve for lambda. Now, if you guys remember from last time, my characteristic equation was given by the determinant of a minus lambda I equal to 0. Okay? Determinant a minus lambda I equal to 0. So let's find out what a minus lambda I is. Okay. Now, if you remember from last time, what's going to really happen is that I'm going to have A minus identity matrix times lambda, right? We're going to add those two things together, right? And what really happens is that what you're going to have is that you're just going to be subtracting lambda along the main diagonal. So what you end up getting, you can check this out for yourself, is you're going to have 1 minus lambda, okay? Negative 1, 0, 1 minus lambda, 3, 0, 3, 1 minus lambda. So you're going to get this minus lambda occurring along the main diagonal when you do a minus lambda I. Okay, this is what's going to happen, right? When we do that subtraction. This is what we did last time, if you remember. We did a minus lambda I. We did it very slowly, but not 2 by 2. And I'm just kind of skipping that step. And then we want to be able to find the determinant of a minus lambda I. Equal to 0. Now this, we know how to find the determinant of a 3 by 3, right? We can use a diagonal method, we can use a cofactor method. And if you want to, try to do the cofactor method on this one. To see if you get the same thing I get. However, we're not going to do that right now. We're going to actually just use our calculator, right? Just plug it into your calculator, find the determinant of this matrix, right? Into your calculator. If you have one, TI-89, or if you have a calculator that you use on your computer or on your cell phone, right? Type in this matrix, find the determinant of this matrix, set it equal to 0. And what you get when you do this, if you do this correctly, this is what I have. I have negative lambda cubed plus 3 lambda squared plus 6 lambda minus 8 is equal to 0. So minus lambda cubed plus 3 lambda squared plus 6 lambda minus 8 equal to 0. And again, I'm going to use my calculator. There's ways to solve this without using a calculator, right? But just use our calculator to factor this, solve for the values of lambda. And we get that lambda, when we solve for it, lambda is equal to, I have 1, 4, and negative 2. So these are my eigenvalues. Okay. These are the eigenvalues that I get for this. Meaning that when I multiply A times my eigenvector for each one of these eigenvalues, it's going to either keep the vector the same. This is what, since I'm just multiplying by a scalar 1. It's going to stretch it out by 4, right? Because I have a scalar 4. Or it's going to stretch it out by 2 and then flip it in the opposite direction because I have a scalar negative 2, depending on what the eigenvector is. Right? So we need to figure out what are the eigenvectors for each one of these eigenvalues that I have here. What are the eigenvectors for each one of these guys? So let's do that next. So step 2. Find, I want to solve A minus lambda I times B equals 0 for the vectors B. So A minus lambda I times B equals 0 for the vectors B. And this is going to be for each value of my eigenvalues, right? So for each, so I should say for each lambda. Right? Because I'm going to get a different eigenvalue for each I'm going to get a different eigenvector for each eigenvalue that I have. Or we should think so. That's fine. So let's just start from the beginning, right? Let's start with lambda equal to 1. Lambda equal to 1. Lambda equal to 1. Okay. And so plugging into this particular matrix, right? let lambda equal 1, right? That's it. This matrix right here. I'm going to end up with, if I do this correctly, 0, negative 1, negative 1, 0, 0, 3, 0, 3, 0. Did I do that right? Did I get that right? 0, negative 1, negative 1, 0, 0, 3, 0, 3, 0. Okay? Times my vector B, I'll call it ABC, equal to 0, 0, 0. Now notice that this matrix is singular, right? I can do essentially this row and this row. What I can use a linear combination of the second two rows to get the first row, right? Can you see I can use a linear combination of this row and this row to get the first row that I have there, right? So this is a singular matrix. Since it's a singular matrix, I cannot use an inverse, right? This matrix has no inverse, so we're going to have to use Gaussian elimination. Okay. And so I have this 0, negative 1, negative 1, 0, 0, 0, 3, 0, 0, 3, 0, 0. And my line here going across. Let me use a different color. I'll use red here. Right here. So when you do Gaussian elimination on this, we reduce row echelon form. This is what I end up with. I think it's 0, right? 1, 0. 0, 0, 1, 0, 0, 0. Oh, I have another column of zeros. Okay, like that. What does my system look like? What's this system? You gotta be careful here. You gotta be careful. So let's see. I think that this is gonna be B equal to 0, right? And C equal to 0. That's my system. That's my system. What's my solution, though? My solution is going to be, remember, it's going to include A, B, and C. We know B and C are both 0. What is A equal to? And if you said that A is anything it wants to be, then you are absolutely correct. It is going to be T, our parameter. Okay. And I can write this in vector form. A, B, C. 1, 0, 0, T. So I can then say that my fundamental eigenvector, right? I can pick any scalar multiple of 1, 0, 0, but I just choose 1, 0, 0 to be my fundamental eigenvector for lambda equal to 1. So I'm going to put that here. So eigenvector for lambda equal to 1, my eigenvector is 1, 0, 0, or any scalar multiple of 1, 0, 0. I can essentially think of this as a fundamental eigenvector, right? This is one I can, essentially from this eigenvector, I can get every other eigenvector, right? Just by multiplying my scalar multiple. Right? Let's go to the next one. Lambda equal to, in this case, 4, right? Lambda equal to 4. Again, we're going to do what we did before, right? We're going to do the same thing we just did, right? We're going to plug in 4 in for lambda, right? So we have, in this case, I think, negative 3, negative 1, negative 1, okay? 0, negative 3, 3, okay? We have 0, 3, negative 3 times ABC. Eventually, once you get good at this, you can skip steps, but I wouldn't skip steps now, just to make sure that you understand where all these numbers and values are coming from, right? Make sure you understand how we're getting A, B, and C, right? Don't skip steps until you actually understand completely, right? That's never a good idea. I wouldn't skip steps regardless, right? You know, guys, I'm pretty picky about that. Again, this matrix is singular, okay? So that means it doesn't have an inverse, so we have to use Gauss-Jordan elimination. And now notice that we wanted it to be singular, right? That was the whole reason why we're doing it. That's how, the whole reason why we have the determinant A minus I equals 0, because we wanted this matrix to be singular. So it's exactly what we want it to be. So let's do Gauss-Jordan elimination. So I have 3, -1. Let me not write too small, okay? 3, -1, -1, 0. 0, -3, 3, 0. 0, 3, -3, 0. The reduced row echelon form of this. Do I have here? I gotta make sure I have the right thing. If I did it correctly, and I don't have it on here. It should be, if I did it correctly, what we should have is, I think, what should we have here? Going across, I should have let me double check. Let me get back with you guys. I forgot to write this down.